Okay, as I mentioned, statistical techniques use probability to draw inferences from sample data. And so if we have a population, we take a sample, we administer a treatment, and then we can look at information with the treated sample. What we would be interested in is what's the probability of obtaining a certain mean from this group of 25 rats. So oftentimes what we're interested in is the likelihood of a particular mean less than or equal to 5%. And so that's why we have z-scores of 1.96 and 1.96, because anything beyond that this tail is going to be 2.5% and this tail is going to be 2.5%. And so essentially, if we were to obtain a mean over here or over here, the probability of obtaining that mean given our population's mean and the standard error, the likelihood would be less than 5%. And so oftentimes that's what we're interested in whenever we are comparing treated samples to non-treated samples or to populations. Okay, so take a second to answer this. A random sample of 16 scores is obtained from a population with a mean of 50 and a standard deviation of 16. If the sample mean is 58, the z-score corresponding to the sample mean is 2. So you would want to find the standard error, which you know is the standard deviation of the population divided by the square root of n, 16. You would take that and you would put that in the denominator of how to calculate z-scores for sampling distributions. Decide if these are true or false. False and false. A z-score of 3 is extreme and is very unlikely. And individual samples will likely vary from the population mean. Why? Because of sampling error. And how do we measure sampling error? Standard error. Okay, that concludes chapter 7. I would suggest reading the book, but email me if you have any questions.